Yeah, hi everyone. My name is Vinay. I want to introduce about my project in this first introduction. In this project, I worked on implementing a neural network model for time series data forecasting. So the project involved several steps, starting from data collection and pre-processing, building a RNN, simple RNN model, and eventually redesigning the model with LSTM layers to improve its performance. In part one, we have a time series data. So I have taken a electricity demand data set. So actually, the electricity demand data set is a time series data set containing the individual household electric power consumption of a single household in France over a period of 4 years. The dataset consists of a single text file containing 275,215 observations and 9 variables. The dataset was obtained from a domestic residence in France and was recorded at a one-time interval between December 2006 to November 2010. The data was collected using a Zigbee wireless network, and each observation corresponds to a minute of recording. So the variables in this dataset include date, so the date on which the observation was recorded, time, the time at which the observation was recorded, global active power, the total active power consumed by the household in kilowatts, and global reactive power, so the total reactive power consumed by the household in kilowatts. Next is voltage. The average voltage it is in volts, so supplied to the household, and global intensity. The total current intensity, yeah, the current, so it is measured in amperes, so consumed by the household, and submetering one. So this submetering one is consumed by the kitchen, and submetering two, and the active energy consumed by the laundry room, and there is submetering three. So this is consumed by electric heater and air conditioner. So the data set is available on the UCM Machine Learning repository website in the given link. So the dataset can be downloaded from the website as a single text file. So the time series span of dataset is 4 years from December 2006 to November 2010, and there are 2,75,000 different data points in the dataset. So the data in this dataset is structured in a table separated format, tab separated format, sorry. So with each observation, a new line, and each variable separated by a tab. So the first two columns of the dataset contain date and time of the observation, while the remaining columns contain various electric consumption measurements. So that dataset contains some missing values, so which are basically denoted by a question mark character. So now we are going to part 2. So it is regarding a simple RNN sine wave data. So in the data collection and pre-processing for this project, I generated a sine wave dataset with added noise using NumPy. So the dataset had 1,000 data points with a timestamp of 0.1. So the data was then normalized between 0 and 1, split into training and sets and testing sets. So with 80% of the data we are using for the training, and remaining 20% of the test data points we are using for testing. So here, so for generating the sine wave data set, so we have imported pyplot from matplotlib, from imported matplotlib library, and that we imported pyplot. So and we represent it as a PLT, and again we are importing numpy as a NP. So since we have num points, like we have 1,000 data points, so which are in that we are using 80 points for our testing and 80% for training, and 20% is for testing. So, and we have given X variables. Like if you go in search, if you see the X label should contain 0 to 10. So it starts with 0 and ends with 10. Num points indicates, and Y variable indicates the sign value of the sign value and random variables of this thing. And now if you go to the plotting area, so we want the figure size should be 10 into 6. So we have given plot figure, and we want plot X values and Y values, and the color should be blue. So color is equal to blue, line is 2, if the style is, and label, we want to label it as a sine wave. So it's label, and we have kept the title as a sine wave with noise. So for that, we just use the command plt.title. And if you want to uh, headings like for labels, so for X label, we have given X values, and for Y label, we have given Y values. And we have kept them less than at upper right. So location is upper right, that less than thing. And we set the grid is equal to, so we will get that grid. And we kept the plot show so that we can get the data of, we can get the sine wave. And so again, for training the module, we have using 80% of data points for training. So that is the reason we are trying size is equal to integer of num points into 0.8. And then we are training size. So we are using train x is equal to x values of into train size. So these are the few commands which we are using to split the data for training and testing things. And then reshaping and data, we use these two commands for reshaping and the training and testing data for RNN model. And to compile this thing, you use model.compile plus is equal to MSC optimizer is equal to ADTA. So to train the RNN model, we use the command history is equal to model.feed train x train score y f course is equal to 100, validation data is equal to test x comma test y. So this is one, we'll use new things. Now we are evaluating the RNN model. So for this thing, we are again importing MATLAB, matplotlib pilot as a PLT, and for to evaluate, we are running this command test underscore pred is equal to model dot predict test underscore x. So after predicting that, we want to know the results, right? So for getting those results, we have used plt.plot test command, whatever it is. So test y label equal to true, like means what is the expected thing it is, and plot the test label is called predicted. So the another one is it's the prediction one. So it will show us what is predicted one, what is the true one, what we got and what we predicted. So the blue color indicates the true one, what we did, and the predicted one is what exactly it should be. So, and this is the architecture of neural network. So we have input, and we in this model architecture, the input layer takes a one-dimensional input, which is a value of sine wave. And then the simple RNN layer has 64 neurons, which allow it to capture patterns in time series data. Finally, the output layer is fully connected layer with one output neuron, so which predicts the next value in sine wave. So after generating a sine wave dataset and building a simple RNN model using Keras, we split the dataset into training and testing sets, where 80% of the data was used for training and the remaining 27 was used for testing. We then compiled the trained RNN model using training data with the model being optimized using the ADTA optimizer and using mean squared error as a loss function. So the model was trained for 100 cores and the validation was set as the testing set. After training, we evaluated the RNN model, the test data, by predicting output values and comparing them to the actual values. We use the predicted values and the actual values to create a plot that shows the comparison between the two. The resulting plot shows that the model was able to accurately predict the sine wave pattern of this test data with some minor deviations due to added noise in the original dataset. Overall, the results of the simple RNN model shows that it is capable of accurately predicting a sine wave pattern with added noise and can be useful for predicting simple time series data. And now the third part is LSTM neural networks. So before going to question 3.1, so how I want to give a brief explanation about LSTM neural network. So LSTM means long short-term memory neural network. It's a type of recurrent neural network that are designed to address the problem of vanishing gradient in standard arguments. So the vanishing gradient problem occurs when the gradients used to update the weights in the network during training become very small, making it difficult to train the network effectively. LSTM networks were introduced by Skimmander in 1997 and have become a popular technique for modeling sequential data in various applications, such as natural language processing, speech recognition, and image captioning. So the key innovation in LSTM network is the use of memory cells that can store information over a period of time. These memory cells are controlled by gates that regulate the flow of into out of the cells. The gate consists of sigmoid and element-wise multiplication operations that allow the network to selectively forget or remember information based on the input. So there are three gates in LSTM network. Like it's a, they are mainly forget gate, input gate, output gate. So forget gate means it decides which information to forget from the previous memory cell state, and input gate it decides which information to add to the current memory cell state. Output gate, so it decides which information to output from the current memory cell state. So LSTM networks can be trained using backpropagation through time, BPTT, if I'm not wrong, so which is an extension of backpropagation algorithm used to train standard feed-forward neural networks. During training, the gradients are calculated with respect to the weights in the network and used to update the weights using an optimization algorithm such as stochastic gradient descent. So, and also LSTM networks have been shown to be effective in wide range of applications and have been used to achieve state-of-art results in many tasks such as language modeling, speech recognition, and image captioning. However, they are computationally expensive to train and may require large amount of data to achieve good performance. But when coming to the vanishing gradient problem, refers to the situation where the gradient of loss function with respect to the parameters of the neural network becomes very small during training, making it difficult to update the weights effectively. This can occur in recurrent neural networks such as simple RNN because the gradient is propagated through time by the recurrent connections, causing it to either shrink or grow exponentially as it further back in time. When the gradient becomes very small, The network becomes resistant to further learning and the model's performance can plateau or degrade. On the other hand, the exploding gradient problem occurs when the gradient becomes very large during training, causing the weights to update with very large magnitudes. This can lead to instability in the training process, and the model can diverge or fail to converge to a good solution. So, the simple RNN neural networks has some limitations, including difficulty in capturing long-term dependencies limit to memory capacity and a tendency to suffer from vanishing gradient problems during training due to the nature of recurrent connections. The simple RNN is limited in its ability to retain information from earlier time steps, which can make it challenging to model complex temporal sequences. So the long short-term memory neural network is designed to address the limitations of simple RNN and provide powerful solutions to both the vanishing and exploding gradient problems. The LSTM introduces a memory sense that can store information over long periods, allowing it to learn and retain dependencies between events that occur far apart in time. The key innovation of LSTM is the using of gating mechanism which controls the flow of information into and out of the memory cell. As we discussed previous, I have mentioned here about there are three gates about forward gate, input gate, output gate. So these gates are implemented using sigmoid or hyperbolic tangent activation functions, which range between 0 and 1, allowing the model to selectively forget or remember information uh, from previous time steps. Additionally, the LSTM includes a separate input gate, output gate, and forget gate that can be trained to learn which information can be stored or described. This is what we have discussed previously as well. By allowing the model to selectively control the flow of information through the gates, the LSTM can avoid the vanishing gradient problem by maintaining the gradient flow through time, even or more many time steps. Additionally, the gating mechanism can help mitigate the exploding gradient problem by preventing the weights from updating with very large magnitudes. As a result, the LSTM can provide powerful solutions for modeling complex sequences and has been outperformed simpler and on a variety field of tasks. So if you see, this is the diagram. This illustrates the architecture diagram of an LSTM cell. So here, the memory cell is represented by horizontal line across the top, and the gates are represented by sigmoid activation functions. So the input gate determines how much new information to let into the memory cell. The forward gate determines how much old information to forget, and the output gate information determines how much information to output from the memory cell. So the cell state represented by the horizontal lines runs right through LSTM, allowing information to flow from one step to the next. So before going to the next thing, I want to elaborate more things about the disadvantages and what are the advantages of LSTM. So when you're talking about the advantages of LSTM, so they have ability to remember long-term dependencies. Like they are designed to handle the vanishing gradient problem, which makes it easier for them to remember information for longer periods of time. So this makes them a well-suited for tasks that require modeling long-term dependencies, such as handwriting recognition, language translation, speech recognition, and also they have ability to handle input sequence of varying lengths. Like they are capable of processing input sequences of varying lengths, which makes them useful in situations where the length of the input sequence is not fixed. Like this can be driven to like this can be used in this uh, they achieve this thing because of that forget gate, which allows the LSTM to selectively remember or forget the information. So, and they have ability for different types of input data. Like they can use it to a wide range of input data, including images, text, and speech. And also, they are a robustness to noise. So they are able to filter out noise and relevant information in the input sequence through the input gate, which controls the amount of new information that is added to the cell stream. And when coming to disadvantages of LSTM models, uh, they are more complex than other types of RNN due to their multiple gates and memory cells, which can make them training and interference slower and more resource intensive. And sorry, and also they have lack of transparency. So these are very difficult to debug and diagnose when they don't work properly. This is because the internal working of the model are hidden and difficult to interrupt. We are going to part 4, using critical thinking and experience with time series datasets. I propose several changes to the above network to improve its performance. I redesigned the network by adding LSTS layers, introducing dropout layers to prevent overfitting, adjusting the input sequence length, and changing the batch size and number of echoes for training. So see here in this with LSTM, I imported pandas, imported NumPy, and imported matplotlib, and I imported TensorFlow. I also import from this Skyline processing for and also imported min max scalar. So for downloading the data set, so we have given the URL, date frame, and we are giving it to the CSV form, and we are using Python engine. So for data set is equal to, we have given data for frames. So when data is equal to data set S type float 32. So we got these values. So again from Keras, we imported sequential things from Keras layers. We imported dense from LSTM dropout, and we imported math, and we imported TensorFlow, and we also imported mean squared error from sklearn metrics. So for reshaping data, we have used these commands like create data set, and from we have given data X and data Y. And for IM range, like length of data set minus look back minus 1. Again, we have given look back equal to 1, so its look back will be equal to 1. So and A equal to data of I into I plus look back 0, and it will return things and will train X and Y based on the create dataset function. So for compiling the model, we use model.compile to measure. So Adam and loss is equal to mean squared error. So we will train the model by the following command: model.fit train X, train Y, equals equal to 100, batch is equal to 32. So we'll train the things. So for making predictions, so we use these two formats, like train predict is equal to model.predict train X, test predict is equal to model.predict test X. So invert predictions to original square. So for those things, we have used the following commands like train predict is equal to scalar dot inverse underscore transform train predict. So the train predict will be how this scalar dot inverse dot transform, and train y is equal to scalar dot inverse transform np dot array train y, and we are reshaping it. And again the same things again for test predict. Whatever the thing we have done for train predict, we'll do for the same for test predict. So now we are able to calculate root mean square error. So root mean square error means we can try math dot square root of mean square error for train y and train predict. The same time test score is equal to math dot square root of test y and test predict. So now we'll get the print of these two things. We'll get the train score and test score. So we want to forecast the future values. So future data is equal. We'll give some arrays, dot array, and future data. We have used things to forecast the future values. So we need to again invert predictions to original scale. So forecast is equal to scalar dot inverse transform forecast. So it will print. So if you want to print the forecast values, you'll get these things. Now, so comparing network performance based on the redesign of LSTM network in part 5, what we have designed and the core parameters upgrade to 8, we compare its performance to the original network in part 4. So the original network in part 4, like what I designed, is a single LSTM layer with 32 neurons, no dropout layer, and a sequence length of 50, a batch size of 32, and was trained for 100 IPMs. It achieved a mean square error for approximately 0.14 on the test data. So the redesigned network had two LSTM layers with 64 neurons each, and a dropout layer with a rate of 0.2, the sequence of length 50, and a batch size of 64. It was trained for 100 cores. It achieved mean square error approximate of 0.24 on the test data. So the results show that redesigned network performed better than the original network. So with a higher MSE on the test data. So the addition of second LSTM layer to more neurons and a dropout layer likely help the network capture more complex patterns in the data and prevent overfitting. So the longer training period was allowed the network to converge to a better solution. So overall, the redesign of LSTM neural network is resulting in a significant improvement in performance, indicating the importance of carefully choosing the architecture and hyperparameters of the network. I compared the performance of the original RNN with the redesigned LSTM model. The redesigned model shows improvement in performance with a lower mean square error and a smoother plot predicted was actual values. So here I want to conclude my project. So overall, this project providing an opportunity to gain experience with neural network models from time series data forecasting, and the results showed that LSTM model with the dropout layers and optimized hyperparameters can improve the accuracy of forecasting models. Yeah, thank you.